So this is part D. So part D says starting with the energy balance equation, enthalpy as the function of temperature and the integration of the cat equation 107, and then we're going to find derive this as a function of temperature, and then use the root to find the adiabatic temperature. So first thing that we know is our chemical equation is going to be that CH4 plus O2 oxygen, and then going into water, and then can you give us CO2 2 Okay. I am doing part D. So part D says starting from the energy balance equation, enthalpy as a function of temperature, and then the integration of the cat equation 107. And then we want to derive the function of temperature to yield the adiabatic temperature. So the first thing that we want to do is do our chemical equation. Our chemical equation is going to be definitely CH4 plus oxygen, which is CO2. And then this is going into the flame. And then this is going to give us CO2 plus water, H2. I'm doing part D. So part D says that we want to. Okay, I am doing part D. So part D says starting from the energy balance equation, enthalpy as a function of temperature and integration of the cat equation 107. And then from that, we want to derive a function of temperature whose root yields the adiabatic temperature. So the first thing that we know is the chemical equation. Chemical equation. Methylene, which is CH4 plus oxygen, and this is going to be CO2 plus H2. So from this, we can see that this is imbalanced. So we're going to put 2 in front of oxygen, and then we're going to need a 2 in front of water. So we know that. We also know that this is a combustion reaction. We have oxygen. So let's just draw what is happening. So first, we have this. So we have our methylene coming into this, and then we have a flame, which is burn, also a combustion reaction. And what's coming out is going to be our CO2. So this is the inlet of that. Inlet out. Okay, so first we need to know is some of our initials. Our initials are here temperature. Our temperature in is going to be 298. And then our temperature coming out is what we're going to try to find. So we're trying to find that. So from this, let's derive our enthalpy equation. For our enthalpy, let's do enthalpy as CO2. CO2 is going to be equal the heat of transfer of CO2 and the heat of transfer at 290. And then this is going to be plus our specific heat of CO2. And then we're going to do our temperature coming out, T for now, minus our 290. And then we know this, so from our derivative, from our integral of specific heat, and this is going to be percent temperature. 298 is going to be. Okay, so now we know what our enthalpy equation is, and let's do our energy balance equation. So our energy balance equation. So the energy that's changed in the system, so differential amount of internal energy plus the differential amount of kinetic energy plus the differential amount of potential energy. So this is of our system, and then this is our differential amount of change of our energy coming into the system plus differential amount of change of the kinetic energy coming into the system plus potential energy coming into the differential amount of heat coming into the system times the differential amount of mass coming into the system. And then we are going to subtract this by the differential amount of change of energy coming out of the system plus the differential amount of change of kinetic energy coming out of the system plus potential energy, the differential amount of potential energy coming out of it. And then this is going to be multiplied by the differential amount of mass coming out of it. Okay, and then we have some other energies that are going to be our differential amount of non-slowness. And then we're going to have the differential amount of change of the heat transfer. Okay. So one thing that we know is we're doing an adiabatic flame. Adiabatic means that there is no heat transfer. So transfer, that means EQ. And we also know that this is a steady state. A steady state means that our energy change of the whole system is not going to change. So that means that the first part of the entire energy change of the system is going to be zero. And we also know that from our equation here that there is going to be no height difference. So that means all the potential energy is going to be zero as well. And then we know that for the steady state, the kinetic energy of the system is going to change. And then our nocturnal work. So, what do we have? We have the energy coming into the system multiplied by the differential amount of change of mass coming into the system minus the energy coming out of the system times the differential amount of mass coming out. So, we can make this equal. We can flip the sign, make this equal 0, so this should equal each other. And then one thing that we do know is that differential amount of change coming into the differential amount of mass coming into the system equals the differential amount of mass coming out of the system. So that means we can just divide by both sides by the differential amount of mass change, and it will cancel out. So then we have the energy into the system equals the energy coming out. Okay. And then I'm going to integrate the CAD 107 on the computer. Okay, so part D, part 2 says assuming this is 100%. Okay, so at part D, part 2, it says assuming this is 100% combustion, calculate the adiabatic flame temperature for natural gas comprised of 95% mole of methylene, 4% of moles of ethylene, and then 1% of moles of N-propane. And then this is all burned with a 200% of excess air. So Let's write out our chemical equations. So first, we're going to have methylene, which is CH4, plus ethylene, which is C2H. Okay, so let's do the chemical equation. So the chemical equation is going to be methylene, which is CH4 plus ethylene, which is C2H6, and propane, which is going to be C3H8. Okay, so and then this is a combustion reaction, so we're going to have oxygen, which is O2. So to figure out all of like the ratio between the carbons and the hydrogens, we can do a matrix. The matrix is going to be, so our matrix is going to be our carbon on the top and then our hydrogens on the bottom. So our carbon of methylene 1, carbon of ethylene 2, and carbon of propane 3. And then the hydrogens are 4 and 6. And so this is going to be a 2 by, so this is a 2 by 3 matrix. And then on this side here, what we're going to multiply by the composition, we're going to multiply it by the percentages that it's abundant, right? So on our sheet, it says that it is 95% of methylene, 95, right? The first column is going to be our methylene. And then our second one is going to be our ethylene, which is at 4%. And then our N propane is at, and then this is a 3 by 1 matrix. So when we multiply these, then you cancel out the 3, right? So it's going to be a 2 by 1 matrix. And the 2 by 1 matrix is going to be a carbon and a hydrogen. And so this is how we're going to solve for the abundance of carbon and hydrogen. Do for part D, for part D. So the first thing that we want to do is our chemical equation. We're going to use Wolfram alpha to do that. So our physical properties. So let's do 107 right here for our equation. It is y plus b, and then it's going to be times c divided by t divided by the hyperbolic sign of c divided by t all squared plus d times e divided by t over divided by a hyperbolic cosine of e divided by t, and that is all squared. So we go from alpha. What we do is let's first do just a regular. We're going to use that define adiabatic temperature. What we want to do. So we have first divided by we have hyperbolic, and this is all so. is so annoying. This is going to be C times the cotangent of the hyperbolic, and this is going to be C divided by T. Since there's no hyperbolic, the next thing that we want to do, let's just copy and paste this as our full equation. Um, E times is going to be cosine of E, and then partial. Okay, so this is what we get for this. So we're going to use this equation. Yeah, so now since we know that, it's going to be from the getting up side. So from the module import, and we're just going to take this piece of context in our equation. So the first thing that we want to do is this solution. And then we are going to increase. So after we define equation, so we're going to do the integral of our specific heat. And so since we since integrated our 1 of 7 equation, we're just going to do the specific heat of that. find the well, turn is we're going to read so what we're going to put that integration. Specific key. So for integration right here, so the first thing we want to do is dot, and then we're going to do the CP, specific heat of radial gallons of we're going to do A like this by T, which is our temperature, and then we're going to do P, heat of radial gas, then we're going to do this of C, and then oh no, this is sorry, that's time C 1 divided by tangent of the hyperbolic. And then we do C of T, so and then we want to do divided by, so that's our heat of D times the heat of E times tangent hyperbolic specific heat of E divided by T. This should be a side here. Oh, and before we do it, we have to initialize our P. So before we initialize our P, we have to do P equals and then our product are going to be properties are going to be we're going to have ethylene and propane. And then we want oxygen. Side. Water and nitrogen. Okay, so after we have our intercept, after we have our integral of the CP, now let's calculate what it's going to be for the enthalpy. This one's going to be for the, we're going to define a function for enthalpy. Enthalpy is going to be H and T. And then it's going to, we have the interval of C. Now we can do this. be just substitute our what we're going to return is the heat of formation of an ideal gas plus, then we're going to have the flow of heat, which is going to be temperature, and then it's going to be the control specific heat, and it's going to be 290. Okay. So after we do this, what we want to do is we're going to just made about find the composition of the field and position of the field. So we know is excess air 200. So the next fuel composition is going to equal it will empty just the adverse A, and then so this one is going to be 1 carbon, 2 carbon, 3 carbon, and then we need the hydrogens, which is going to be so then that's going to be our fuel composition, and so then our N matrix. Oh, yeah, fuel composition. Sorry, this is our N matrix. N matrix. Just put this. Our fuel composition is going to be percentage of moles of methane, ethylene, and propane. So this is going to be this has an abundance. Methylene has 95% mole, and ethylene has 4%. What we're going to do, so we're going to multiply these two together, and when we multiply them, we're going to find the number of hydrogens and the number of carbons, right? So carbons and going to equal, so M, and then also multiply the tree of the fuel composition. So after for hydrogen and carbon, so then we're going to use this to figure out our chemical equation. I mean our thing that we know is that's going to equal the number of carbons. And then we know the number of 12 is going to equal the hydrogen divided by 2, since there are 2 hydrogen and oxygen and water. So after we know this, we're going to have to do the stoichiometry of oxygen. So what we're going to do is say this is going to equal so what we did with our chemical equation, so we're going to get the number of carbons that side plus water divided by 2. So that is okay. So after we have that, now we're just going to have a regular N2O. And then so what we're going to do is we're going to multiply this by the exotherm. So let's do our number. So we're going to have our N position. Okay, and we're going to multiply this by 1 times the exotherm. We find out the air that's in the exotherm. After we have that, we know all of our H2s and everything fits. So the next thing that we need to do is air. The thing that's most abundant with air is nitrogen, not oxygen. So we have to account for the number of nitrogen is going to equal the ratio between nitrogen and air, which is nitrogen, which is 7, 2, sorry, 79, 21, multiplied by our. So the next thing we want to do is know all this stuff. Let's do our moles in, let's do our moles out. What we're going to do is we're going to do a fuel position. And then we're going to do an array. And this is going to be comprised of our and of oxygen. Just oxygen. It's going to be comprised of our oxygen. So it's going to be comprised of 2, our oxygen. It's going to have 0, carbon dioxide, 0, water, and it's going to have some nitrogen. So all of excess. The carbon dioxide and the water are kind of excess. So in here. The moles out now is going to be MP A. So our red is going to be, so how much methane? We're going to have 0 of methylene and 0 of propane. And then the next one we have is oxygen. So our oxygen is going to be our O2 times our. And then the next one is going to be our carbon dioxide, which is going to be CO2. And the next one is going to be our water, which is 2. And then we're going to have our nitrogen, which is N. We don't have to do that. Um, okay, so now that we know this, what we're gonna have to do is here. Okay, so after we have so the next thing now we want to do is going to be our energy difference. Energy difference. So fine. Sure. And so we're going to do dot multiplication. What we're going to want to repeat and be dot multiplication. And this is going to be dot multiplication of we're going to have and then we're going to have FP, Hw4D. This is the temperature that's coming in, and then we're going to call the of our out times the enthalpy. Okay, and then lastly, root of our one. Also, and this is we wanted this is divided by Okay, so if we look at over here, we wanted to do 1 plus the excess air, so just 1 plus the excess air, and then we have over here, we're going to do the oxygen of the stoichiometry times the excess air over here, and we over here want to divide by 1,000 because it's giving us CP in kilomoles, and we're going to have this back into moles. So we need to divide it by 1,000 so that these can convert correctly. So you have to divide this by 1,000, and so if we go here and we just should enter, which is for x is equal to 1.14 e to the third. And that should be our flame temperature for 80 battery.